Hello students, hope you are all doing fine. Today we will discuss one important topic in your solid state physics syllabus, Hall effect. Which was discovered by Edwin Hall in 1879. That is before the invention of electrons. Now, before going to the definition of Hall effect, let us discuss some observations. For this, first of all, take a slab of conducting materials. It may be metal or may be semiconductor, and that semiconductor we take so that the majority charge carriers will be electrons. Then if we apply an electric field, there will be a current along this direction and the electrons will be drifted along this direction. We all are aware with this situation. This is the direction of current, and say Vd is the drift velocity of the electrons. Fine. Now what we will do? We apply a magnetic field. Magnetic field in a direction perpendicular to the direction of the current flow, along this direction. So that means magnetic flux are outward from the plane of the paper. Sorry. So if we draw it like this, say this way along x axis current and along z axis our magnetic field, and along this direction. So we have a current carrying conductor or semiconductor, and we apply a magnetic field in a direction perpendicular to the direction of current. Then it is observed that there is a voltage. This voltage will develop across the two surfaces of the specimen, and we can measure it. This voltage is known as Hall voltage, and the whole this effect, that means development of a transverse electric field when a conductor carrying current is placed in a magnetic field which is perpendicular to the direction of current flow, is known as Hall effect. The voltage is known as Hall voltage and the electric field produced is known as Hall field. We denote it by EH. So this is what is known as Hall effect. When a current carrying conductor is placed in a magnetic field which is perpendicular to the direction of current, an electric field will be developed in a direction perpendicular to both direction of current and direction of magnetic field. So now let us see what happens, why it is so. So we know the electrons, due to the application of magnetic field, the electrons will experience a force. We denote it by Fm, which is given by the formula is Q into V cross B. So V in our case it will be Vd, and it is along negative x direction, cross B, it is along k cap. So, minus minus plus E V D B, I cross K will be minus J cap. That means the electrons will be deflected along negative y direction. So, what we find, we have the specimen. Here is in the bottom surface there will be accumulation of negative charge, in the upper surface there will be positive charge. So, a potential difference is created which we measure as VH. So, this downward deflection of electrons can be determined without using this mathematics, by using Fleming's left hand rule. So, according to which you may remember Fleming's left hand rule. If we stress the middle finger, forefinger and thumb of our left hand side, left hand in mutually perpendicular direction, then if the index finger points towards the magnetic field, central finger points towards the current, then the thumb will give you the direction of force. So, you can apply it like this, it will be like this. So, we can see that the electrons will move along downward direction. So, there will be accumulation of negative charge in the bottom surface, consequently there will be positive charge on the upper surface. So, there is a potential difference across these two surfaces. Therefore, we get what we know as Hall voltage. Now, come to the electric field. Force on the electrons due to the Hall field, we write it as Fh is equal to minus E into EH, and Hall field will be along this direction from positive to negative, such that the electrons will move along upper side. So, deflection of electrons will be downwards due to magnetic field and upwards due to Hall field. At steady state, these two will be equal. That means, Fm is equal to Fh. So, E into Vd B, this will be again along negative y direction. So, if we consider the magnitude, it will be E into E. So, E cancel out, EH is equal to Vd into B. So, we can see that Hall field is a function of magnetic field. Now, if N is the number of charge carriers per unit volume, that is concentration of charge carriers, then current density will be equal to minus NeV due to electrons, NeVd. So, from say this is equation 1, from equation this is equation 2. From equation 1 we can write EH by B is equal to VD, and from equation 2 we know VD is equal to minus Jx by Ne. So, EH by B is equal to minus Jx by Ne. So, we can write EH by B to Jx is equal to minus 1 by Ne. This is known as Hall coefficient. So, for p type semiconductor, RH will be 1 by P into E, because for p type holes will be the majority charge carriers. So, thus we can see that Hall coefficient gives the knowledge of the charge carriers. So, there are various application of Hall effect, as I have already told you. From the sign of Hall coefficient, the sign of current carrying charge can be determined, and hence semiconductor type can be determined. The concentration of charge carriers can be determined by knowing the value of Hall coefficient. The mobility of charge carriers can be measured directly using Hall effect, because we know mobility is nothing but drift velocity per unit electric field. And this Hall effect has many practical applications. Hall sensors are used in our cell phones, in automobiles, especially ABS braking system, and in our washing machine, and in many more places. So, this is all about Hall effect and Hall coefficient. Thank you.